After over half a century, it is time to return to the moon and use its vast resources as a bridge to countless new worlds. Welcome to Science and Futurism with Isaac Arthur, and I am your aforementioned host, Isaac Arthur, writer and producer of this show and also president of the National Space Society, an organization dedicated to a future of space settlement. And when it comes to settling space, finding a way to set up self-supporting bases on the moon is necessarily always at the forefront of those efforts. After all, if we can't make things work on the moon, the only celestial body within real-time communication distances of Earth, how could we ever hope to make things work on any other planet? At its core, though, the moon is not just a prototype place to try out space settlement, but also the gateway to those other places because it is very rich in resources to mine, process, and refine, but also low in gravity and air, the two things that make getting off Earth and into space so hard. This is why we have done so many episodes on the moon, and will doubtless do many more, and why today we will be focusing on how we get those resources, and in the near future, with existing technologies. And it all comes down to economics and the tyranny of the rocket equation. If I want to put a spaceship on another planet, I either need a vastly better fuel and propellant, or I need to be willing to launch dozens of ships into space carrying a payload of fuel, just to be able to have the fuel to send one of those spaceships off to another planet. That ship isn't moving too fast either. Even if better fuel is found, it is still better sourced on the moon, but so is all that air, water, and honestly anything that we could build there instead of here on Earth. That might get sophisticated as we improve automation and options like 3D printing. For now though, it is okay if we have to fly every sophisticated piece of equipment up from Earth, every microchip or control panel, if we can produce big, thick shielding panels for the ship, or water tanks or water for those tanks on the moon, or simply get the resources there and move them to orbital factories and dockyards near Earth. After all, on the moon we have a power generation issue. There's no fossil fuel or wind or hydropower, but there is a half a month of sunlight followed by half a month of darkness, which makes solar kind of viable, and there are plenty of options for using nuclear reactors there as there is not much worry about radiation. Or rather, the place is already pretty irradiated, so it's not a big concern to add to that. We could contemplate some sort of arrangement where nuclear combined with solar ran a lot of the power-intensive projects at a base for 2 weeks, then shifted to lower power ones. Maybe you smelt metal for 2 weeks and then spend the next 2 weeks surveying for or collecting new ore. We do have a lot of ways to supply power in the dark period too, and for that matter, there are places on the moon that are more or less dark than average. Some crater bottoms are perpetually dark, or nearly so, and lava tubes too, whereas some crater rim walls, especially far from the equator, get much longer periods of light. Those craters and lava tubes are of immense interest to us as resource sites too. Now when we talk about building a lunar economy up and extracting material from there, it is worth noting that this is not pie in the sky. Carissa Christensen, CEO of Brycetech, says the annual investment in the lunar economy is currently around $10 billion a year. This is principally government funding, and Project Artemis is around $7 billion of that. But it means we are, and have been, putting billions into R&D focused on the moon, and by we, that does include both private sector spending and other governments. The Canadian Space Agency, CSA, and Japanese Aerospace Exploration Agency, JAXA, are both big partners on Artemis. Incidentally, for the raw facts and figures, I'll be drawing heavily today on John F. Kross's 2022 Ad Astra article, The Lunar Economy, as this episode is intended to be how we get stuff off the moon economically this century, not in the more distant future. So while we might one day mine helium off the moon for aneutronic fusion reactors, for today, we're assuming we don't have any new power generation technology beyond minor modifications to adapt stuff we already have to be functional on the moon. Same for other technologies. It need not be something we have streamlined or even achieved mass production of, or even built an official prototype, but it does still need to be solid tech. That said, a little later in the episode we will dip a bit into harder lifts like a lunar mass driver for getting cargo off the surface. That technology is pretty solid, but it does still have some hurdles to clear, and more to the point, it represents a pretty big piece of infrastructure. And our other limitation today is that we're not really contemplating mega projects. Our biggest limitation on getting to space, and then getting to the moon from there, and finally getting things off the moon, is fuel. And the majority of the weight of the fuel isn't actually the fuel itself, but the oxidizer we burn with it, which is typically oxygen. The downside of rockets is they can't be air-breathing because there's no air off Earth, and even making an air-breathing rocket for use during travel through the atmosphere is often considered impractical, though designs like Sabre for the Skylon spaceplane seek to make it otherwise. Whether or not they succeed in that effort, it does not help once you're in space or on the moon, because you need that oxidizer, and it is literally the supermajority of that ship's mass, outmassing every drop of fuel, piece of ship, and item of cargo combined. Oxygen is heavy, and our two major rocket fuels are liquid hydrogen and kerosene, both of which combine with oxygen molecules to make water, or water and carbon dioxide. A water molecule, H2O, may be 2-to-1 hydrogen to oxygen atoms, but that single oxygen atom is 16 times more massive than hydrogen atoms, and water is 89% oxygen by mass, while carbon dioxide is 73% oxygen by mass. So even just being able to produce our oxygen on the moon would let us save massively on return fuel for any lunar trip, or for shipping anything off the moon for orbital construction. We also need oxygen to breathe, and so looking at how we get oxygen on the moon will be our first topic. And the first step of that is finding oxygen, but amusingly, that's the super easy part. For a place where there is no air, we tend to think of getting oxygen as hard, but oxygen is the third most abundant element in the universe, and the most abundant element on the moon. 42% of the moon's mass is oxygen, tied up in the rocks like silica, silicon dioxide aka quartz, much as on Earth, where oxygen is the most abundant element in our crust and the second most abundant overall, shortly after iron, of which there is a vast quantity in our core. So finding oxygen on the moon is easy, you literally can't walk there without tripping over the stuff. Getting it out of the rocks is trickier though. This is a lot of the reason why hidden deposits of ice in craters or lava tubes is very interesting to us in exploring the moon, as it takes considerably less energy to get oxygen out of water or ice than out of rocks like silica or alumina, which includes sapphires and rubies, or lime, which you might have had to get to clean out your bathtub if you have hard water. Plus, the process also frees up that hydrogen in the water. You can then burn that hydrogen and oxygen right back together into water as a rocket propellant. This is a very simple process, but takes more energy to separate it than recombining it is going to get you, which is why we don't just burn water as a fuel on Earth, but it's a good way to make an energy-rich portable fuel for rockets or for rovers or smaller satellite facilities. If you have a big, bulky, stationary power source, like a nuclear reactor, or several acres of parabolic mirrors focused on a solar thermal tower that could produce tons of fuel and oxidizer during those 2 sunny weeks, and then lie dormant thereafter till the sun rose again, letting you produce a ton of fuel and oxidizer in the meantime, at a rate of about 13 million joules per liter or kilogram of water to be separated, though probably a decent chunk of that would be lost to various conversions and inefficiencies. In the absence of readily available water though, we have an alternative to electrolysis, and that's metalysis or cracking rock, which is generally about 45% oxygen by mass on the moon. This takes a lot more energy, varying by the rock type, and instead of getting oxygen and hydrogen, what you actually get is some metal plus oxygen, which is a plus too, as we want to be able to mass produce steel or aluminum or titanium or silicon there, not just air. There is a $1 million prize from NASA for the first team to demonstrate a method to extract 5 kilograms of oxygen from simulated moon rock in 8 hours or less, which works out to 15 kilograms or 33 pounds a day. That might not sound like much, and indeed it is not for fuel, but it is all the oxygen you need for several humans to breathe during that time. We go through a little under a kilogram a day per person, 0.84 kilograms or 1.85 pounds on the space station, and presumably the consumption would be similar on the Moon. Around 15 years back, Derek Frey of Cambridge had put together a reactor that could do about a kilogram of oxygen for 142 megajoules, which is an order of magnitude higher than electrolysis of water, but was producing metals as well, and that would work basically anywhere, on or off the Moon, on some asteroid. For context though, a rocket booster might easily go through hundreds of thousands of kilograms of oxygen to get off Earth, and tens of thousands to get off the Moon. So if I wanted to get 10,000 kilograms or 10 tons of oxidizer produced every day during a day cycle on the Moon, we are talking over a trillion joules of energy, or 16 megawatts, to produce about 7 kilograms or 15 pounds of air per minute. Enough for an 80-person team to breathe for a whole day produced in 1 minute, or enough for a modest daily launch of a roughly equal weight of cargo off the Moon, meaning you could be running a depot somewhere producing refined metals that are launching using the oxygen released during the making of those metals. 16 megawatts is both a lot and not much. A couple months back we looked at various small modular reactors for nuclear energy, and the smallest module we discussed there was a 20 megawatt design by Last Energy. On the solar front, there is no air in the way on the Moon, so a whole bunch of shiny aluminum parabolic dishes pointed at a solar thermal tower should have no problem providing at least 100 watts per square meter of actual electricity, and a good deal more in terms of heat that might be used for assisting processes for separating rock. So a field 70 meters in radius should do the trick. One of those alternative oxygen creation methods is to heat rock to above 900 Celsius, and many metal forging processes are heat dependent, so energy being lost to heat in the usual flow of making electricity can at least be partially productively repurposed. We also have magma electrolysis, where you melt a lunar regolith by running electric current with it, liberating oxygen at temperatures of 1400 degrees Celsius or 2500 Fahrenheit. Given that making big shiny metal panels shaped as parabolic dishes out of native aluminum is not that hard of a process, one could imagine landing with some pre-built ones or a reactor and using that power to build more, in-situ bootstrapping of energy. As a minor side note, during the daytime on the Earth side of the Moon, it is usually nighttime on part of the planet, so power creation on the Moon, without air to interfere, could plausibly beam energy back to either Earth itself during Earth's night phase, when Earth-based solar doesn't work, or to various satellites and facilities in orbit of Earth but currently in its shadow. Every little thing that might make money on the Moon or decrease losses on surplus production is one more thing that makes lunar settlement viable. This is definitely a thing of the next couple of decades too. Citigroup analysts are expecting the annual revenue of the space industry to hit $1 trillion by 2040, which isn't that far off anymore, and they're predicting a 95% reduction in launch costs by then. This is not assuming any new technologies, just anticipated ones making expected progress at streamlining and improving, paying off the research costs, and scaling the production of the technology up. One of the notions suggested for scaling up fuel production on the Moon would be setting a guaranteed price for a time, several $100s a kilogram. At that point in time, someone can rely on a decade of steady revenue, which makes it feel less risky of an investment. But if we imagine a single parabolic dish or photoelectric solar panel around a meter across that was steadily producing 100 watts on average for a decade, then under electrolysis we would be able to produce over 2,000 kilograms of rocket fuel by electrolysis, or 200 to 300 kilograms of oxygen and a similar amount of metal. If you're expecting to make several $100s on each of those kilograms, then you're looking at somewhere around a $100,000 return off that single panel or dish. Such a panel might only mass a kilogram or even less, especially first-generation ones brought from Earth, which might then get to the Moon for under $1,000 a piece and recoup that investment in a month or two. I should also note that our options aren't just electrolysis of water or metalysis or cracking of rocks. We also have some carbon dioxide on the Moon, and we are getting pretty skilled at separating carbon from oxygen. Carbon is quite valuable too, and needless to say, carbon dioxide is handy for plant growth on the Moon, which would reduce food you need to bring in. As another minor side note, since gravity is small on the moon and there is no air or wind, your panels and dishes can be large with relatively little structural support. Your big issue is cleaning dust off if it gets on there, which would mostly be from astronauts walking around or from rovers merely about to do errands. You can potentially be sticking 10-meter wide panels atop telephone poles, tall but skinny supports. And given the low gravity, it is not that much work if someone needs to climb a ladder to one either. One critical thing to building anything on the moon is that every bit of structural support can be vastly weaker and thus lower in mass, and all of these factors reduce the cost. The exception to that is storage tanks, since any vessel under pressure on the moon actually needs to be a bit tougher than on Earth, where we at least have one atmosphere of pressure pushing back already. And this is one of the reasons why molten salt techniques for generating and storing energy are nice on the moon, as molten salt is not under any pressure, and thus does not need to be sturdy like a steam engine or turbine on the moon would still need to be. Molten salt approaches also potentially allow oxygen production as a byproduct. So using molten metals to produce air and generate and store heat is attractive on the moon, where insulation is easier anyway, and this might be getting energy by nuclear or by solar thermal farm or solar photovoltaic, and possibly a mix thereof. Running power cords on the moon between facilities isn't terribly tricky either, nor is avoiding the dark cycle by just having some power-beaming satellites orbiting the moon, and given that space-based power production might be one of the big industries of the moon, they may have relatively cheap access to it. Solar thermal and nuclear are both attractive options on the moon, but silicon photovoltaic cells remain a strong option there too. Blue Origin has been working on Blue Alchemist, their solar panel design made from lunar regolith simulants. Their reactor produces iron, silicon, and aluminum through molten regolith electrolysis, running current through the regolith, and produces oxygen as a byproduct, with silicon that's been purified to 99.999%, and they have now made working solar cells from this simulated regolith. The process they developed may have applications back home too, as it's entirely electricity-based and appears to be much more environmentally cleaner than currently employed methods for getting silicon. There's a lot of silicon on the moon too. Silica, or silicon dioxide, is the most common compound on the moon's surface at nearly half, followed by alumina, dialuminum trioxide, at around a fifth to a quarter, and then a rough three-way tie between lime, which is calcium oxide, iron oxide, and magnesia, or magnesium oxide, each making up a tenth or so of the lunar surface compound, depending on the region. Titanium dioxide comes in at a few percent, and sodium dioxide at a bit under a percent, and everything else at far lower concentrations. But that means from a practical standpoint, we have an unlimited supply of oxygen, silicon, aluminum, iron, magnesium, titanium, and sodium. Note that hydrogen, carbon, nitrogen, potassium, and phosphorus, all fairly critical to life and farming on the moon, are not casually abundant and may be easier to truck in initially. We do not have to get everything in situ. If you can get 90% of your raw mass on the moon instead of Earth, that massively alters the space economy. For one thing, it also creates one, since you'd have all that industry and freight capacity to and from the moon that would make other industrial and economic sectors easier to start and piggyback off of. It is important to keep in mind that we really don't know the best way to get resources off the moon yet, other than that many techniques from Earth probably still apply well, while other crazy options might work too that would never work on Earth. For instance, you might use a roving mining facility that trundled around to good small deposits, then basically went over top of them, suction cupped over them, then blew out huge inflatable mirrors the size of football stadiums to act as a solar oven on that spot, vacuum up the superheated gas and centrifuging it into its constituent bits. Such a tactic would be utterly insane on Earth, and probably isn't the most efficient approach on the moon either, but even so, it would actually work. I would say your processor might just be a vacuum cleaner rolling around the moon's surface, but vacuums don't work on airless planets, so just a scoop would have to do. That low gravity and lack of air also makes it fairly easy to move cargo around, so you don't really need to contemplate onboard refining. Rather, we can expect surveying drones to wander around looking for the best deposits of the desired material, and then for something bigger to come on by and get it, probably by either that scoop or a sweep approach, maybe by an actual robot hand-picking up loose rocks of a desired material. This might not be on the moon's main surface either. Those craters in many cases are going to have some nugget of meteor in them, which might be a nice individual find, and those immense lava tubes might be great places to mine too. I don't want to give the impression that our options are limited to just dumping energy into rocks to melt them down. I like that one as a general one-size-fits-all approach that's easy to explain to folks new to the topic, but in all probability it's one that will rarely get used. It is essentially the brute force energy approach, which is mostly handy for its simplicity. Also, it may be needed in some cases simply from restrictions. I am strongly of the opinion that the Outer Space Treaty can be ignored as a placeholder awaiting something more informed and useful, but it is entirely possible it or some future modification or successor of it might see restrictions on resource utilization. We might see a ban on fission reactors there or power beaming from there or limits on mining techniques that involve throwing lots of high-speed dust or releasing certain vaporized materials or quantities thereof. I think your two biggest non-fuel demands are going to be steel and aluminum. Truthfully, we don't need much oxygen to breathe, and much would be recycled by growing some supplementary plants and herbs for fresh greens and flavor. Aluminum is abundant, but the preferred source is assumed to be anthrite, 1 calcium atom, 2 aluminum, 2 silicon, and 8 oxygen, and would typically be obtained by grinding anthrite out of anorthosite and then magnetically separated from magnetic anorthite. The FCC Cambridge process is a favored process, using electrolysis of the ground-up anorthite in a bath of molten calcium. After the oxygen comes out and the calcium melts into the bath, we would expect the silicon to remain solid, and the aluminum, being denser than calcium chloride, would drip out of the bottom for collection. The process would probably need to be fine-tuned for a lower gravity environment. It would anticipate yielding 46% oxygen, 20% silicon, 19% aluminum, and 14% calcium by mass. A parallel approach works for removing iron and titanium from ilmenite, found plentifully in Lunar Maria, and is magnetically separable, and gets you 37% iron, with the balance of the mass equally split between titanium and oxygen. There are other ways to get aluminum out too, like raising it to 2000 Celsius in a vacuum, and again, any of these materials can be taken down to the atomic level with sufficient application of energy. The trick for optimal processing is finding that Goldilocks spot of effort, time, equipment, and energy, and that will be different for every material. But an abundance of sunlight, lower gravity, and a lack of air are the 3 critical factors likely to shift which processes work best on the moon as opposed to Earth. Also, here on Earth, we have vast supplies of water as a coolant or solvent, and a surplus of manpower and replacement components. Stuff built on the moon needs us to contemplate cooling options besides air or water, and must be very durable and potentially need replacement components that can be easily 3D printed. Remote control and maintenance options are also viable on the moon, as it's close enough that signals lag on a couple of seconds, not minutes or hours as with the rest of the solar system. Also, while we talk about it as a great place to get oxygen or aluminum off of, valuable elements like gold or platinum are every bit as plentiful on the moon as asteroids. Speaking of aluminum again though, while it is a high energy cost material to make, it is a handy one for production on the moon for many reasons, but maybe most of all, early on, as an alternative to water. Hydrogen and hydrocarbons aren't the only things that burn when combined with oxygen, and aluminum is a great example of that. Aluminum will burn with water to produce alumina and hydrogen molecules, and vice versa. You can use hydrogen molecules to take alumina and turn it into aluminum and water. This fuel is called ALICE, short for aluminum ice rocket, and is likely to be a great in-situ fuel any place where ice and rock are both plentiful, like the outer asteroid belt, or moons of Jupiter and Saturn. But if the moon turns out to be a hard place to get water or hydrogen from, we can't combine iron oxide and elemental aluminum to instead produce aluminum oxide and elemental iron, and release a lot of energy in the process. This is also known as thermite and is already used in some rocket thrusters. Producing thermite on the moon and processing into rocket fuel is a relatively simple process, and I like it as an option not because it's any sort of miracle fuel, but because the stuff is going to be plentiful any place you land. Even places where no in-situ water is a stark reality. And it's not just aluminum either. Boron, chromium, magnesium, silicon, titanium, zinc, and others all have pyrotechnic combinations with some sort of oxidizer, which isn't just molecular oxygen, but a number of common oxides. So if the moon is where we're getting a lot of our fuel and raw materials for expansion out into the solar system, using fuel systems that can be refilled at the destinations or waypoints is a good plan. Carrying return trip fuel with you is beyond brutal, again the tyranny of the rocket equation, and likely to suck any profit or practicality out of any venture needing to bring stuff home in quantity. Amusingly, your rocket thrust is partially vaporized metal, so it's not a horrible idea to contemplate shooting things out of a long tube or tower like a gun barrel, where your metallic and oxide exhaust can be partially reclaimed. Again, there's no air on the moon, so even some lava tube shaft, repurposed and shored up to serve as a long runway, is a possible option. This would still apply to water or any alternative fuel like methane, and I think we hear these options discussed more because they are a lot easier to make and use, and we have grown increasingly optimistic about getting water on the moon. Long term, the moon hasn't got much water or hydrogen, so it's not a good source for it for ages to come, but it's a good boon for starting up, and water and hydrogen are stupidly common elsewhere in the solar system, and can be fairly cheaply imported back in later generations. But if it turns out we are wrong about the hydrogen and water supply on the moon, it just shows we have different options, and also shows us our pathway to mass producing metals there too, many of which are magnetic and would be very easy to magnetically propel out of a mass driver. We also do not need to achieve the super high velocities that we have to in order to get off Earth, nor do we need any sort of megastructure tens of miles high for the tube to open out of above the atmosphere, since there isn't one. Done with the right timing, things launching off the moon already have a lot of the extra delta V they need to get to a more distant destination, or vice versa, have their velocity dropped enough to make an orbital insertion around Earth or to air brake down to Earth relatively cheaply. We might one day have big orbital installations around the moon, including lunar elevators or orbital rings, but early on we can probably get away with a launch tube running over the surface that only has a tube for the sake of keeping dust out, and thus need not be very substantial. A human ship aiming to achieve low orbit of the moon, at around 1 mile or 1.6 kilometers per second, only needs an acceleration track long enough for 160 seconds of 1g acceleration, something like 80 miles or 130 kilometers of track. Or alternatively, a 4g acceleration of 40 seconds, which would be a rougher ride comparable to your typical rocket off Earth, but only need a track a quarter as long, 20 miles or 32 kilometers. And a cargo launcher sending relatively dumb matter, just sheets of panels or ingots of metal, probably could get away with 40 Gs or more, a 4-second acceleration down a mere 2 miles or 3.2 kilometers long. And sure enough, you might just leave this out in the open on a flat spot and have a robot run down the rail before launch to take any dust off from the last one. In terms of power, this isn't a trivial amount either, but it requires no propellant and avoids the rocket equation, so if you're flinging an object into orbit of the moon at 1.6 kilometers per second, you are probably able to pull that off with a mass driver for an energy cost of a few megajoules per kilogram lifted, making it a good deal less than electrolysis to make a kilogram of fuel from water at 4 times that cost, or cracking oxygen out of rock at 50 times that cost. Your freight bill goes way down. Longer tracks or higher accelerations could send you off the moon with all the speed you need to reach your target, though timing would be absolutely critical in such cases. Thankfully, there's no weather windows and delays like we often have for launches from Earth. This is why, while Mars is often contemplated for colonization, or even Venus or Titan or some asteroids, the moon is always the best place to get your start. From there you can stop building and fueling spaceships on the cheap, with barely enough fuel to get a ship to another planet, and with barely enough radiation shielding to keep the crew from dying. With the moon as your source for fuel and building materials, we can pre-stage huge amounts of supplies to destinations before a human ever gets there, and send them faster and on bigger and better equipped and shielded ships, all supported by vastly superior near-Earth orbital facilities, industries, and habitats. In this way, the moon becomes our gateway to all those other worlds and the stars beyond. It seems like after over 50 years we're finally truly on the road back to the moon, and while that time gap after Apollo was disheartening to go through, it is a reminder that to obtain huge goals often means working for a lifetime. The same is true of personal learning too. You don't just become an expert one day. The secret to achieving huge learning goals and staying sharp for a lifetime is learning a little every day. It's also why many dreams never get off the ground. The billion-dollar startup idea, the invention that's going to change the world, or the career you know you would love, because getting the skills and knowledge to make them happen takes effort. But here's a secret to beating the odds and actually achieving your goals: learning every day on Brilliant.org. Brilliant is the best way to learn math, science, and computer science interactively. They have thousands of lessons, from foundational and advanced math to AI, neural networks, space, rockets, and more, with new lessons added monthly. Brilliant's visual, hands-on approach is such an effective and engaging way to learn. It makes building a daily learning habit easy. Interactive learning has been proven to be 6 times more effective than passive learning, like watching lecture videos, so Brilliant helps you learn by doing. Create programs with drag-and-drop coding, interact with charts and graphs, and play around with many stunning visualizations. Brilliant makes it easy to build a daily learning habit, and you can try everything Brilliant has to offer for free for a full 30 days by visiting brilliant.org/IsaacArthur or clicking on the link in the description, and the first 200 people will get 20% off Brilliant's annual premium subscription. Incidentally, I'd imagine many of you have noticed by now that we've been doing some short-form content, a mix of original material like the Quasar Canon and clips from some of our compendiums. I'm not sure if that's a permanent feature of the show or not yet, but I figure I need to release about half a dozen a month for a few months to see what the effect is, and if it's worth doing. I'm also kind of curious if I can explain concepts in under 60 seconds. I'm not exactly known for my brevity, but for anyone who is worried, no, we are definitely not replacing any of our normal content with shorts. This is just added material like our monthly live stream or Sci-Fi Sunday episode, or image polls to help pick future episodes. Regular episodes on Thursdays are still what this channel is focused on. Speaking of that, next Thursday, July 13th, we'll move on to the idea of moving cities, from those floating through the clouds to those on massive tank tracks or even legs. Then it'll be time for a mid-month Sci-Fi Sunday episode, Robots and Warfare, and a look at the role drones and autonomous machines might have in the future, along with finding out what the first rule of warfare in the future will be. After that, we'll discuss whether or not life forms might be based on ammonia instead of water, and what that might look like. Then we'll continue our look at the future of warfare with dropships and planetary invasions or boarding actions. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show on Patreon, and if you want to donate and help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service, Nebula, along with hours of bonus content at go.nebula.tv/IsaacArthur. As always, thanks for watching and have a great week.